Forest Survey. But he was talking about there's a place in Peru, I believe, but they're talking about megaliths. They're talking about running into things that don't make sense and are out of time. But apparently, like on the South American continent, the finest megalithic work. And he just posted this recently. And this polygonal joins that they have on it, just really impressive. See some of them here. And pre-Inca.
I think that the joints are made like that on purpose so that it's almost like when you're doing tile or you're laying bricks, you juxtapose them.
Mm-hmm.
But they came up with better ways of how to interlock them than typically how we do it, but it takes more time. I think they realized
these are like
it reminds me of almost earthquake preventative in a way.
But they're like 60 tons each. You know?
Wow,
this is the
ridiculous.
thing. It's like, how did they do it?
Welcome to the November 4th edition of the Electric View. I'm Neil Thompson. Today we have Jim, Eugene, Edwin, Heather, Buddy, Robert, and David. We will be discussing some oddities of electric archaeology, terrestrial and astrophysical plasmas, and the different ways they express themselves. Please like and subscribe.
And they have these curvatures in there, you know.
Let's go back to the conversation we had before about how people maybe possibly used to be giants, or that there were giants. Like people were larger. Because it seemed like a suitable idea to stack stones this big for people who couldn't feasibly move them. We don't know, you don't work with something you can't use, so that's inaccessible for the worker. Got to be kind of user friendly, right?
Yeah, unless you want to make something really big, like, something really big to awe people.
Well, yeah, but they did that in Rome, and even then they didn't use bricks that big. These are, and there is.
It's one thing to do a straight line, but to do this kind of curvature, you can see. There's some here that you can really like that.
And what are the knobs for?
It's like a dovetail joint.
What's that?
It's like a dovetail joint. It's like a key, so they lock.
Uh-huh. Yeah. And I think it's almost because I want to say they knew that it was going to shake, because the earthquakes and whatnot. Is there many earthquakes around this area? Possibly now or before?
It looks like there was, and there was worldwide. I mean, every single structure looks like the big like problems that one of the things that they did was they either made them out of the living rock, like that, or they were heterogeneous. They had rocks of completely different sizes and shapes so that there was no shear lines. Later on, in solving an engineering problem of a similar nature, not using this technique though, they invented what was called the herringbone pattern, which was stacking bricks in alternate ways and cementing them together. And this allowed the structure to have no definable break joints. And that's what they did to build, for example, I think it was Brunelleschi and a cathedral that he built way back in. Well, he didn't build it. It was started like 100 years before he got to it. And then he was commissioned to cover the dome. And to do that, they had to overcome the problem of, besides lifting the stones and everything like that, was to do it without, because it's going to take, decades. So it's going to take decades to make, because it was like 100 meters across. Well, at least 160 feet at least. It's just huge, though. And try to put a dome on top of it and then not use any supports underneath. So that's how he did. That's what he invented and how he got past the problem. He had faith in his engineering. This is a different ballgame. They're doing something here that almost seems like
it's granite. you know.
But it looks like it's been molded.
Right, exactly.
And I wonder what, and I think that this is one of those things that lead you
But I mean,
to
this
wonder.
type of fit, you know, and that's they were intending that. It seems.
Well, it looks like it's sort of like got squished and sort of pushed out a little bit on top of another stone.
Mm-hmm. What he was? It's Brian Forrester. That's the guy, right? And
Yeah.
and he what you can kind of see from as they're going in, and that like this is the Inca work where it's really rough, but these are the
They did what they
megalithic
could,
stones.
yeah.
They did what they could, yeah, exactly. But
So since we're talking about,
it looks like it was there was a catastrophic event, and then the Inca propped it back up. So that's at least what he's positing. So.
It's a good posit. Go on, buddy. What were you saying?
I don't want to take us too far off a topic, but I mean it is the topic we're talking about. If we wanted to talk about this in more or whatever, but yesterday Aurora and I went rock collecting in our local quarry here, and we found some amazing specimen. And I kept having this feeling that I was going to.
Go ahead.
It's in Kensington Metro Park here. There's a natural rock quarry in Michigan. So yeah, we can get right on this if you want to look. Kensington Metro Park. It'll take you somewhere else because there's a lot of Kensingtons in the world. Kensington is also the name of a place in Peter Pan.
Okay, right. Okay, so we'll
been there.
We'll avoid that
one. So this is one of the most amazing finds that I've ever found in my life. I'm a lifelong, you could call me an enthusiast, a geological enthusiast. I've always collected rocks. So it's one of the things that I prefer to do if I'm going outside. I'm either going to go collect sticks and make some wands and some walking sticks or some rocks. So we're out. There's a rock quarry. If you look, probably that looks like that spot. No, go out. That's the golf course.
Okay.
Yep. See right there, that rocky, that sandy towards the right. Yeah, right in there.
Right in there. Okay.
Yep. So this is where I'm looking. We found meteorites in here. We found petrified wood, trilobites, a lot of different types of things inside here. A lot of beautiful agate. So yesterday I kept having this feeling that I was going to find something extremely rare or extremely weird. And I found this rock, and there was this, here, let me change my thing into viewer and turn it around. Okay.
Okay.
So
okay.
This is what I think this is. I've never heard much about ancient meteorites that hit the Earth before and then got sandwiched in between sand and aggregate layers, sedimentary layers and whatnot. So this is a sedimentary rock. It was formed by layers and layers with pressure, with mud. And if you look here, this was sitting right here directly in this spot right here. And it was like a circle, an inclusion, clearly. So I open up the inclusion, I crack it open, and it's metallic, it's metal. And I think it's an ancient asteroid, or an ancient meteorite, I mean. I haven't found any types of metal like this. It might even be poisonous metal. There's a lot of types of metal out there, but I've never seen anything like this. And it's flattened, and it has a perfect spot inside of this older rock, which I've never even really looked into old asteroids or things like that, or meteorites. Sorry, I keep saying asteroids, but they're meteorites. So I took it home, and this is the meteorite test. You put a magnet to it, I put a really strong magnet to it, and I have one right here, a diaminium magnet. And I put it on there. Nope. It's not magnetic. That doesn't, I don't know what that, it doesn't necessarily connotate it's not a meteorite. It could have lost its magnetism, but there's clearly, the entire thing is metal and metallic, and it's heavy, and it has that line going through it that you can see.
Does that layer through the whole thing?
Yeah, that layers through the whole thing. If you take this other piece through this, and then here's little pieces, other pieces, the top piece, and another smaller piece. So I want to get this tested. Never seen anything like it. So that's my rocks for this evening.
Cool.
And I was so excited. I actually found brown onyx. It's a black stone that's like glass, and it is glass. I've never seen brown onyx before. Usually it's black, so that's a rare one.
I found that yesterday.
Yeah, so I'm so excited. We're gonna go right now, and I'm gonna put my headphones on and go do some more rock collecting.
Nice. What's you have one in the center there that's kind of a rounded triangle.
This one?
No,
this one?
Up. That one, yeah.
That is the exact same kind of stone that I fractal brand, so that'll have a nice electric arc going across it once I zap it correctly. A lot of these are the exact same types of rocks where you open them up, and inside of them they're mudstones, and that's what you look for. You look for rocks that you can open up, and inside that is the mudstone that you can actually fractal brand or electrocute. Yeah.
Do you find arrowheads at all?
On the shore, you can find some arrowheads. I found a few on the shoreline. This is another one that I think might be some sort of metallic inclusion, but you see, they go together. You take them apart, and it seems like it's some sort of iron. It's definitely got traces of iron surrounding it. This is another.
If you put your thumb on it and rub it a little bit, does it get like a specular? A little bit like a metal. Kind of looks like it's some.
Not necessarily on that one. Here's a rare pudding stone because the entire thing is red, and the tiny little amount of white that's on it is rare because usually it's mostly all white and a tiny little bit of red. So it's a good one. But yeah, I'm going to get out there and, if I find anything else, I'll let you know.
Cool. All right. Excellent.
Mm-hmm.
We always like show and tell. So it's good.
That's always a good thing.
Yeah. So, Michigan. What's going on with Michigan? Michigan's like a magic place, I think.
Michigan geologically, it's a pulp. Go ahead, Heather.
We have three Michiganders in our group here, so this is an indicator, right?
Yeah. But somebody told us that last weekend that Michigan was full of that the Michigan magical community was very, very powerful and very much together. So it's something you don't think about, but
right.
Power, the fresh water.
It's that mitten thing.
It's lake effect intelligence is what we call it.
Lake effect I see. Right. And you got both
Henry
sides.
Ford.
You're in Michigan, right?
Yeah, you got Henry Ford, Madonna, Eminem, Jeff Daniels,
right?
Motown, Lake effect intelligence, and techno,
right?
Techno,
right. Very cool.
So going back to the idea of that with Neil and the amount of pressure change because the ocean comes up so much, the tide rises and falls so much around your area, does the barometric pressure go up and down a lot because of that?
Well, you're the only person who's ever said that. I'd never even heard about that until you mentioned it. Which is cool.
Oh, dude, it's one of my favorite things. I mean, if you think about change and transition, you got to look at places on the Earth that are extremely variable by their changing. Like, what's the name of where you live? The
Bay of Fundy.
Yeah, that's some cool stuff. People risk their lives out there.
Well,
collecting.
Only if you're silly, I guess. I mean, if as long as you can walk away from it, you're fine. I mean, it doesn't come in that fast. It takes 6 hours, so yeah. But it does miles and miles of ocean to go walk across. Yeah, which is nice. Although there's some dangers, I guess. There's like sometimes there's pockets of gas underneath and stuff that can cause. Well, I guess. It could cause you to be swallowed by the sand, I guess. That would be probably bad.
Sinkholes?
Yeah, those type of things. But
giant clams will eat you.
Is this happening right over the water? What's going on here?
I ran across this just as we were getting together for this, but this one just as you, I don't know if you've ever watched like a pot of water boiling. Yeah, I'm sure everyone has, but I think there's certain parallels here to watching it, and then it's time and scale. So, but you watch how these clouds work.
Watched pot never boil.
That's what I was going to say. I'm like, you must have a lot of extra time, David.
I do.
Hey, everybody, I'm here. If you think all of us sit there and wait for water to boil, no, you're wrong.
I know, yeah, I know, yeah.
I try not to watch.
You caught me. You're right. But this whole obvious time lapse, right? But this whole action, that's pretty amazing to me. Anyway.
Well, I love that it just happens in one spot though, and barely moves.
It's pumping too. Play it again. It's pumping. It's going whoosh, whoosh, whoosh.
But I don't know if this is over top of that water or is it further beyond?
Yeah, I can't tell. I don't know if is this there's a little bit of a variation there, so I'm not even sure if that's a body of water as on the horizon.
Yeah, that was just my first instinct. Yeah.
Yeah. So anyway, it was cool. I thought it was cool. So who joined us? We just got the.
I don't know. I thought I heard Eugene's voice, but I don't now.
Yeah. And Krakatoa. Have you seen this going on? This has been interesting.
I saw the BBC remake. No.
Yeah, no, I know. But this one's been pretty active, and then we see the lightning comes in here pretty dramatically.
That's the son of Krakatoa.
This is the sun. Look out! Yeah.
This is the little tiny one that was left over when the last one blew up. Yeah, I guess it was 1883.
No, the last one was just a prelude.
I think lightning might be a lot more simple than we think.
Well, it's
like
simple.
It's like static. It's like just like static electricity. When you got stuff moving, it starts striking like clouds, volcanoes under your blanket.
Yeah, I just took a bunch of clothes out.
That's like the standard explanation for why it happens is because of the static charge built up in the particulate matter as it's being ejected, and then it rubs together and causes lightning, just like if you're pulling your blanket off you and your static playing.
So it's already Electric Universe verified. Whooching!
Well, actually, yeah. I think the big difference is that
it's electric. Yeah, lightning is electric. That's well as stupid.
Yes, we now know. Thank you, Ben Franklin.
That is the key.
The key is not just charges, though. When you introduce electromagnetism or moving charge, you put in magnetism, and once the charges are moving and they have a magnetic field, that's why they can become tubes as we see here. But does that
Well,
studying what these tubes are is literally what Jim is doing, except on the grand scale. You know,
right.
well, he's thinking about the whole thing like as us, like one of those lightning bolts that shot from between the clouds there, or between just right there, for example. Now,
Gotcha.
thinking about that as our solar system being part of that tube, and it discharging from point A to point B, how does the discharge take place over time? And how does the electromagnetism affect the current and so on? That it's a lot different than just because we're at a different scale. We're seeing things in slow motion compared to just like this, very quick, and sparks flying between bed sheets and doorknobs and so forth. But they are all electric arcs.
That breakdown voltage has to exist, right? I mean,
that's correct.
That's the defining point of the thing, right?
And that's very interesting.
So
how do you build up voltage and so forth?
And then what's the mapping of those of that? You know, the voltages in space.
And you know how hard it is just watching them try to build a fusion reactor. You know, they're like, oh yeah, well every time we build it, the magnetism gets screwed up and it doesn't follow our math. Oh really?
Right.
What a surprise. Right. You know.
Did anybody see the post from Peter Mungo Jupp about the Rabaul eruption in 1980, where the arc of lightning went between two different volcanoes, like 10 kilometers apart?
No. Let's see.
They were arcing towards each other.
Oh.
Wow.
It's in the Electric Archaeology. I'm looking at it right here. Who posted it? It was
Can you pop the link in?
What's that?
Can you pop the link in the chat?
Oh yeah, I'll try to. I'll do it on my phone here. I just got here. I was traveling. We went up to the parents. My aunt is coming in from Pittsburgh. We're
nice.
Here.
Okay.
Yeah.
Cool.
That's why I was going to be late. So I was traveling.
Okay. No problem. So as you're doing that, this was a pretty. I don't know if you caught the latest version of Space News, but it's pretty good. Let's see if this is the one. Yeah, here. Recommend this one to check out if you get the chance. It's they're kind of looking at the big picture overall movement of the movement itself. It seems like so great. Is this the one? It's interesting anyway.
Well, this is the arc between two volcanoes?
Was it Robert? You still there?
Yeah, I'm still here. I'm just looking. I posted the link from the Electric Archaeology. However, it's just a comment that Peter Mungo Jupp made. I'm trying to look up the actual.
Okay.
I don't think there's actually any picture of that eruption where the arcs are actually going back and forth.
Okay.
That would have been a chance encounter.
Right. And it was back in 1980 where, we didn't have many journalists sitting around waiting for things to blow like that.
With cell phones.
Yeah, I'm actually so happy for this revolution in technology so that we get it all the time. We get to see, earthquake lights now. They're not just a rumor. You see ball lightning now, not just rumor, because every single person is attached to a telephone.
Right. It's a really significant change in perspective.
Well, it's
you've been looking through this little hole, and now it's the whole. Now it's like everyone's.
Well, sprites were reported by pilots for years before we actually get a picture of just one of them.
Mm-hmm.
Speaking of sprites, they're different colors, right? Or is it mostly red because of the element in the atmosphere?
Color usually is determined by the element, yeah.
Is there different color ones, though?
Yeah, red, blue, green.
Nice.
hydrogen, oxygen, nitrogen.
Is there ways that we can particularize like metals and make them glow in plasmas? Like
Yep. Copper glows green.
Because I was thinking if we could like melt it or not melt it, shape it down to monatomic level and throw it in a vacuum tube and create different lights with it. I'm sure it would be poisonous, but neon poisonous.
Well, actually, you can actually buy little packets of that and throw them into fires, and they will change color. The fire will change color depending on what packet you throw in. We sell them up here, yeah.
Yeah, we get them every Christmas, and then when we light the fire in the fireplace, we toss them in and have like little blue spot and a green spot.
I thought they were kind of cool, but yeah, you can get really big ones with like if you watch electrical pinch stuff, you see the green flame shoot. That's because the copper vaporized. The whole wire just turned to atoms. The electricity was so powerful, it just blew it apart. Which is cool. That's how those coin shrinking machines. Have you ever seen that? Where they use the Lorentz force to crush a coin?
Right.
That's it, guys. You gotta get a high-speed camera. Look at that.
Yeah.
Rip.
They've studied this a lot. This is a very interesting one because this is the bow on water because they've studied it a lot. But this often happens. This is often measured, and that's our tetrahedral angle. So that's an interesting window.
Is that is that always that same angle, or is it?
This is how, like when they studied ships on water.
You were talking about that before. And as a guy who always was trying to catch those waves when the boats went by. Not that we could surf in something so tiny. Just it was cool because we were in the water and we were kids. So
right. Yeah, but the you would think that the angle would change depending on the velocity, right?
Well, yeah.
But apparently in the water it doesn't. Here they're saying it does. He mentioned it. The angle is a function of the velocity, but from my understanding, and with if you're talking maritime analysis of this dynamics, the fluid dynamics of water, it's this thing.
Well, it does. I know it changes. Yeah. I know it has to change when you slow down because other waves catch up to your boat. But it's this. I don't know.
It's this angle. It's where these two meet. So
ultimately, it looks spherical to me. Like it's just. Isn't that the same thing as a Bessel function? Right?
Jim, what would you say to that?
It looks spherical, and I'm pretty sure, as far as what I know of a Bessel function, it looks like the same thing going on here. Maybe in the opposite direction as far as the wave fields go.
Is Jim still there?
Yeah. Yeah, I'm not seeing the Bessel function analogy, though, but...
So the sphere's going at this. Yeah, the thing that with that element of the thing that Don Scott brings up, I think it's more the way that we've looked at it. At least I see the Titus Bode analogy of this rotational dynamic going on.
So if you're going faster, they would be stretched out farther, or if you're going slower, it would create a different dynamic, but that's basically the general sketch of things here.
What I'm saying? Yeah. I mean, this is where it's good to keep it kind of open. Is what are we looking at with the Bessel function?
Mm-hmm.
So I see it. I see it spatially. There's a reference. There's a reference with this spatial frequency that you see in this gun going off. I see that with the rates of Mercury versus the rates of Saturn going out to going out to Pluto. This spatial frequency seems to be very fundamental.
I would like to see more solar systems, I guess. I mean, if anything is true with regards to some of the Saturnian cosmology type ideas, then we're the only thing we're lacking imagination when it comes to.
Can't we look at both Saturn and Jupiter as versions of the same thing?
Well,
with their moons.
Oh, okay. In that sense, yes. But I meant with the idea of the system being rearranged recently and everything being thrown into disarray,
and then going back into harmonic.
Well, yes, and what causes it to rebalance itself and so forth, if that's even occurred. But we don't have enough extra solar systems to look at with enough detail, and they're quite far away. So credit that we could even tell their planets around them. So,
right. How do they fall? Do we know, Jim, on the moons of Saturn, the moons of Jupiter? How do they look harmonically?
They have that same spacing. Yeah, that was one of
isn't
it? What's that?
That's a tell, isn't it?
Yeah.
Yeah, one of the first objections was that that to the idea that spacing was just coincidental. That they started looking at moons and finding them. Then they found it in the few extrasolar planets that they found. They think that pattern might be there too, but for sure with moons around the planets, they do that same kind of spacing. So,
well, there's 64 of them around Saturn, or so, if I'm not mistaken, and they follow that exact same pattern. I need to know now. I want to know more. That's very convincing. Oh, there's Pan.
So here's see we're saying. But that's what they're saying. Right? Saturn has been.
There's some ice geysers. Cryovolcanoes, sorry. Whatever they're called. I'm laughing. Right there. But yeah, Saturn has that nice glow about it too.
That looks like it's straight out of Metropolis.
It does, actually. Freddie Mercury should be singing right now.
Oh, man. They got a movie coming out.
That's going to be great, I hear.
So how many are there total on Saturn?
There's a bunch of big ones and a ton of tiny ones.
Mm-hmm.
And I don't know about the tiny ones, whether or not they fit into this, or is it a certain mass that starts making them fit into this this idea?
Uh-huh. Very cool.
That's what it looks like through a telescope. There's Pan again. I love that guy.
This?
Yeah, it's one of those sort of like evidence of concretion type ideas. There's another one that has a ridge as well. Ridges seem to indicate a improper pinch but the pinch wasn't complete all the way around. Like, it didn't have a chance to roll.
Mm-hmm.
It basically just got squashed together, and the pinch didn't last long enough to make it fully round.
Right.
So it's left with this, it's left with the ravioli ridge around it. And there's another, I think it's Oedipus that has one as well. But it's obviously a lot smaller because Oedipus is so much bigger. There it is, at the bottom. Right there. APOD, Saturn's moon, Pan for Gazzini. I don't know why it says Pan, but see that ridge?
That's
I think Oedipus's ridge there. It has it's all the way around. It's around the whole planet. And
right on the equator.
Right on,
or right on it bisects the sphere.
It bisects the sphere, yes.
Uh-huh.
I don't know if it actually rotates in that direction.
Mm-hmm.
Because Pan doesn't. But Pan's also, looks like it's also collecting some dust too, but apparently there are a few asteroids with that same feature, which just gives a lot of credit to the pinch idea of planetary formation. For obvious reasons. Because that certainly doesn't add up to any sort of what was it called? I don't even know the name of the old idea now. Conglomeration or accretion disk. Accretion disk. I mean,
so there's Pan and Pandora.
Yeah, Pandora's another moon. Yeah,
but it's got that thing.
You still think that accretion happens, though, right? You're not just throwing that out of the window because there's clearly a plane where things accrete.
Well, if that plane is caused by magnetism, it's not really accretion then. It's just the Lorentz force pushing them down to the neutral point. Because if they're up too high or they're down too low, they're going to be a higher load in the circuit. So it's going to want to move them to where the rings are, and that's where it's just.
So what would you call it instead of accretion?
I honestly don't know.
Is there a name for it? Because that sounds like pretty demonstrative that it's already happening in the universe.
Well, in the idea that things are with the debris is raining down on top of things, I know that's happening too. I mean, it's happening to the Earth. It's happening to every planet. Seems to have things falling on it all the time. So that I don't deny. It's that kind of accretion. Look at Mars. Pictures of Mars. Just flat for as long as the eye can see, and rocks everywhere. And we were looking at. They were having Anthony Bourdain was on the CNN thing. I don't know, Far Off Places or whatever it's called there, and he was in Antarctica and looking at some of the places there. And one of the things, I was just staying there looking, and he was like, "Wow, this is breathtaking landscape. It looks like another planet." Blah 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 blah. I go, "Yeah, look at all those rocks everywhere." And sure enough, there's rocks, sharp, pointy rocks everywhere. No cliffs for them to fall down. When did they land there? From where did they land? There's no water that came by to roll them around. They're not even rounded. There's probably only been one or two floods here ever, type of thing. So it's just like that, where these rocks are everywhere. Venus is very similar, just rocks. I mean, so yeah, they had to be falling from the skies. There's just really no other explanation. As much as it sounds ridiculous on the surface of it.
This structure here is obviously compelling.
That's Olympus Mons and the Tharsis Bulge, they call it, I think.
Uh-huh.
It's, from the Electric Universe perspective, it seems to be several anode blisters in one spot that stayed there for quite a while. And it seems to be a positive point since it's covered in debris. That red seems to indicate height, and it looks like, as you can see, the stuff that was moved during the large strike that formed that canyon it pulled up material from the green and blue areas and dumped it on the red area over there. So it looks that way anyway. Positive and negative points of the strike, so to speak.
Do you think that sprites are anode tufting? A large example of anode tufting? Because I look at them and I see plasmoids. And, like an anode tuft almost. And I'm also interested to see more examples of anode tufting. David showed that video.
Look at the Sapphire Project. They have lots of videos showing what happens, and you can see them as they crank it up slowly, how more and more tufts begin to form across the ball and everything like that.
I'm interested in like maybe some of the first experiments, or why aren't we doing more? And other people, it's all plasma physics, correct?
Yeah. This is nothing strange. You can see. Well, this is probably going to be cool enough.
I want to research some more plasma physicists. Wow. Yeah.
You were saying,
right, yeah.
That's what I wanted to see. Information at our fingertips.
Looks like a bug zapper.
Yeah, kind of similar.
They're saying those are anode tufts, so I'll believe them. I can't tell what is unless you know what's positive and what's negative, I can't exactly tell the truth of it, which is okay. I'm not judging, but anode tufts are weird. And you get cathode space. There's a whole slew of stuff in the Crookes tube showing, okay, at this point you're going to have this, and there's going to be a layer. Like, as much as they try to remove that by using the right density and the right material in a fluorescent light to make the fluorescent light glow evenly, but you even know that if you go all the way to the little end of the fluorescent tube, you'll notice there's a little dead spot there. That's anode tufting, yeah. But yeah, there's a little dead spot, and that dead spot is caused because there's something you can't get rid of right there. It's called a cathode dead space, and it's where everything begins to accelerate. And so they try to get rid of it to make it an even glow from point A to point B, but they can't. There's just one thing that's stopping them, and that's physics. And these are similar to when I pointed them out in David LaPointe's video, the primer fields. When he was talking about them, he used a piece of plexiglass to keep a bunch of, I think, magnets or metal spheres inside a magnetic field underneath his giant bowl magnet things, and they self-organized. And this is the same type of thing that they do. Each one of them would be like a spinning hurricane vortex, and they're trying to keep equidistant from each other on this thing because they have a magnetic field and so forth.
So are anode tufts plasmoids on plasmoids?
Well, they're definitely plasmoids, I would say, because by definition they're semi-stable. They last for a period of time, and they have a toroidal function. So in all of those aspects, then they would fit the description of a plasmoid as given by Winston Bostick, who first coined the term.
So most of them that we're seeing, though, are existing on current plasmas that we're creating in the lab. So it's plasmas on plasmas, like a fractal almost.
Well, yeah.
And when we see their self-organizing structure inside of the element that David was showing the other day, Krypton, there's clearly an organization, a self-organization process that happens, but it's really just almost like the idea of nothing touches, so it always just kind of maintains a space away from a space because they're individual, and by compactification or minimum compaction, they create these patterns like on a sunflower. You know?
It gets crazy. If you look at the surface of the sun, there's a video that shows the surface of the sun, and with Don Scott. He shows that each of those tornado-like little parts that we see on the sun, they're just the end of one of these anode tufts. And so each of these tufts are squeezed so much together that they cover the entire surface of the sun except for where the double layer breaks down and we get a sunspot. But besides that, they are covering the entire surface of the sun, and there must be literally billions of them. So they can become the surface of the sun, basically, and that's what I think that they are. So,
and what it is pillars of fire. Really, the entirety of the sun is solar prominence, right? Which is pillars of fire.
That's what,
as far as I understand,
it would be accurate to say that. Yes, 2,000-mile tall pillars of fire.
Yeah, which they call solar prominence, right? I thought that was correct.
No, that's just the surface of the sun. That's below the prominences. The prominences are above that. They start, when you see sprites and elves in our atmosphere, they would be like the feet of prominences, jumping out into space and coming back down. Now, if you hit a certain point of material, they're going to be able to pull material off the sun, pull it up, and then, of course, drop it back down, depending on the forces of induction and whatever's pulling these materials along. Once that happens, you get the rearranging, so to speak, of the sun's surface. That's, I believe, an animation of it. And you can see how these little things don't leave either. They stay the same. They stay coherent. That's what I was just talking about, the positive column and all that.
Here?
Yeah, wherever you see that picture in the video.
Right here?
No. You were in the video. Just before you clicked on it, it popped up and showed, because he's describing it. This is where I actually got all this information, is from this video, I think.
Cool.
And you go further and you'll see, the prominence is way up and above the sun itself. The anode tufts are just near the surface. But he uses the tube effect to tell you what part of the sun is doing what. So, but you'll find. So
basically, the geometries to explain the sun and the surface of the sun and the geometries of the plasma flows are toroidal and helical. Basically, this is what I see. That's all we're finding. Is there? I mean, I guess you could use different shapes and stuff like that, but the fundamentals are helicity and torality, correct?
They're like definitely tubes, and they're definitely spinning, so yes.
Yeah. Interesting.
So those are that right there is a whole slew of those anode tufts all packed together. They have no ability to maintain any sort of coherent distance from each other anymore. They're squeezed right up
vertical.
So they're vertical.
So they're just the back.
Wow.
This is just the top of them. Each one of those would be like a hurricane on Earth, all squidged together.
Right.
I found this thing that's kind of it's got an element of it, and we can do like play with a very, very rough simulation of something. Ideally, if I can find it, might not be able to find it. Yeah, but I'll go here instead. Let's see. I was like with David's stuff that he was doing last week. Yeah, no, this Dave stuff from last week. I was playing around with his things coming off.
Some of them look real wicked.
They're pretty wild, right?
Look at a couple hands reaching there.
Yeah, this one.
Oh, he has a little toroid in the middle.
You see, watch these. These are, let me see if I can find it. Yeah, like here.
Yep.
One.
There's a nice spin.
Yeah.
David, he posted some more this week.
Oh, he did? Okay.
Oh my gosh, dude. He posted some more, and like you're showing right here, the helicity. Dude, it's so helical, the new ones that he posted.
Oh, really? I mean, I've been trying to get a hold of him. I've been trying really hard to get a hold of him, and he's like off the radar. And he sent me an email last night. It's like, I'm really impressed with what you did. Because I was impressed with his stuff. Yeah. I just wanted to capture some of it and see it. And so it's like there's positive between, but I think he's been giving, just the addition of those demonstrations are just awesome.
But
So
we should recognize that this is kind of
filamentary.
Well,
Mhm.
I was going to add that this probably is happening there because it's like between three of them. Because remember, he's using AC, so getting this to actually spin is sort of like you have two areas of capacitance, one with a different capacitive charge than the other, and when the power starts pouring on, you can actually get a predominant flow in one direction because the other one is not charging as fast as the other side.
Right.
So you can actually sort of have a flow. So it's
he's probably doing 30 frames a second. So it's like every once in a while you'll catch it. It'll be one direction, right?
But
I think rare. I would say here's a good coherent one. Right?
Yes.
And then you see it. Then you see look at that one, right?
That one might have got charged halfway and then suddenly was
and then turn around.
Yeah. Well, it happens every 16.7 milliseconds or so.
Right.
You can see vorticity in it too.
Yeah, look at this one. Playing around. I'm doing a gradient math.
That looks like a dildo.
It looks like very good. Well, you see where your mind.
Well, there's
is.
some balls at the bottom. I'm sorry. It's
right here. Yeah. Okay. All right. But it's got this. It's got neelicity to it.
It's got neelicity. Yes. That's what I'm talking about. Anyway,
connect the pillars. So, can we discuss why the pillars connect in the non-glow mode? Because when you I love how you've done this, David. They're absolutely beautiful, and when they're shown like this.
This is just rough. I'm just exploring.
Right?
Well, it's almost like what you do, Heather. It's the same kind of thing. You just change it to different modes.
Yeah, but he's got better buttons. He's got all kinds of cool shit.
I have the free lab here. Yeah.
Oh shit. Well, okay. Well, I tried to throw you some kudos. Never mind.
It's all right.
What I do,
thanks, buddy.
it's why I do that you can see what you can. It's to make what's not visible, right? Because
enhance it like they do with Jupiter. Yeah. I mean, that's what they're doing. It's there, but it's just bring it out a little bit.
But see how in this one, the bridge between the two, there's two pillars in the wider form to the left. There's the mainly bright pillar, which looks like the one that Neil was just describing, and then the one that's behind it. And there's a connection, a horizontal connection between those two vertical pillars that creates almost like an H in shape. And it happens a lot. There's two vertical charges that are going up and down independently between the top and the bottom. And then there's a very faint, maybe not glow mode, but there's a connection between the two of them that tends to be lateral. Why does it do that, and why can't we always see it? Like, what is going on there? Do you see it between the two things?
In here?
Yeah, right where you are. Yep, exactly where you just that little light line. Is more defined often, or sometimes, or even in a different. You can see it kind of reaching toward the one behind it in this one.
Mm-hmm.
Why do they do that?
It's a high energy. There's a lot of there's a lot of intensity there, of course. So.
They're attracting one another and still maintaining their attraction to the ground. Why? So what is happening when they do that? Are they taking? Are they sharing? Are they connecting? Why doesn't it take them down? Are they, what's happening in that intermediary point that would be because that could be like when lightning goes this way.
There's so much charge here going on, and anything that we are doing is definitely 100% speculative because there's so much charge moving in between here. We can only see 3 strikes. There might be 5. There might be 7. There might be larger frame here. So, but to bring it back to the sun, we can start to see that, fundamentally these filaments, there's spacing in between the filaments, and there's a geometry of flow inside of the filaments that are even finer. And as they twirl and twist, and to understand this, the filament geometry is very, I think, pertinent to continue our discoveries deeper into plasmas.
Most
And the
definitely.
spacing, the spacing, really, it's about spacing. They're harmonically spaced,
The thing that like keeps on hitting me is you look at like something like this, and there's so much going on in there, and that's where this high speed camera keeps it's beckoning for some reason. Because if you look at this in different time frames, you're going to grab out a bunch of stuff, just like just like doing filtering in a way, So because you can see there's this is, and this bringing this into what are the coherent elements of this, in there. It just ends up looking foggy, but you can see there's other stuff going on in there.
Well, there's probably particle incineration, particle transmutation, and like particle incineration and interaction between the two. Uplift, because isn't he shocking wet clay or something?
Yeah.
So that the water is necessary to even start a spark and to continue a spark, because that acts as a catalyst for the electricity to be conductive.
Mm-hmm.
But without the water, it makes me wonder if something supercharged can be above something that has no water in it and not spark it, and then static electricity ourselves, we shock, we can touch a car, get shocked. There's no water transfer except for on you. We have water in us mostly, it's not inside the metals unless it's wet. But it just made me think about that as well.
Mm-hmm.
What's interesting is not the actual, the thing that causes things to get ripped off, they're not that they're conductive, it's that they're not conductive anymore. They become a hindrance, and the electricity carries them away, because it's basically easier to get them out of the way. The force acting on them pulls them right to pieces. And that's something that, we don't usually deal with electricity on that level. We deal with inside metals, and metals don't move. They have a lattice of ions that stay together, and the electrons flow around them with relative ease. But when you have a discharge here from a metal surface on one side and a clay surface on the other, that was wet, it's going to be wet until there's points where it's like, okay, this part needs to go. It's in my way now. And it's going to start, the stuff on one side is going to ask for material. It's able to move. The part that isn't able to move, the dry stuff, cracks off and is carried along with the current, turned to dust. I think that's just, and then that stuff gets stuck to the outside of this ball again. You don't even see it. It's moving so quickly that it just moves and then just it's turned into fine dust and then redeposited all over that thing in little tendrils. It's just crazy. But to imagine that on Earth, to imagine that on planetary bodies, we know the force exists. We just lack the imagination to actually accept the fact that it could carve the background of that, the Borealis page there or whatever.
Right. So you said he put more up, Daddy?
Did he?
Yes, he did. I shared them on
I've got these. I've got the first. Yeah.
Maybe
between two ferns. He's playing with between two ferns.
It was on Facebook. It was. I tried to send a picture just now, but it's a helical arc, 100%. It's off of part of one of these videos, I think. But it was a still shot, not a video.
Mm-hmm.
I'm wondering if we've ever
I mean, he's pretty psyched about doing this. The one thing, Neil, that you mentioned the other week, where it was the Bostic stuff, or it's a kind of an extension of that, where like the charge goes toroidal, and then it's like the sonoluminescence blast, perhaps. Do you have the name of that video, or what?
Oh, you mean the Eric Lerner's dense plasma focus? That video?
Yeah, I think. Yeah. Couldn't keep a reference to that. But it's Eric Lerner.
While you look for that, I have a real quick question. I was wondering if what supernovas have to do with electrical discharge from body to body of the connected Birkeland currents. Say it's connected to another galaxy, and I was wondering if there's lightning-like discharges that happen right before supernovas, or something. If we've ever seen any Lichtenberg-like lightning-type strikes from any source to any other source, and if we might confuse that and call it something else.
Most definitely, yes. And unfortunately, we have no pictures of the supernova one, because the last time we actually caught a supernova going off was 87, and we only saw it happen after the fact, when we looked up in the sky and went, what the hell is that? And then we started aiming telescopes at it, so no one saw the initial flash. It's rare that sort of thing happens, obviously. And supernovas are very rare.
If it did happen, I mean, if we could just set the Hubble telescope to look at one galaxy for a long-ass time, we would see electric discharge if we were zoomed in at some scale. If it's some sort of prominent type of thing that we suspect happens. Because it might always be the fact of the matter that it's in dark mode plasma, these filaments that are connecting things in strings. But I'm wondering, why isn't there this type of static discharge that we're seeing from the clouds in action, from volcanoes, between the planets in arc mode? Unless it usually always takes place in dark mode. Because we should be able to just focus a telescope for somewhere for a long time and see some sparks. Maybe we're calling it something else. Maybe it is happening, but we just don't know. I don't know.
Okay, well, then, yes, I guess we could probably see something like that. I would recommend what's called a Seyfert galaxy. They're galaxies with incredibly active nuclei in the center. They're glowing positively white. So that would probably be where I would look. Most objects, it seems, and Jim and Edwin could probably either back me up or take me to town on it, but it seems that they're trying to work on the minimum amount of energy expenditure they possibly can. Each load, like the sun, is an electrical load. If that's the case, and each of the planets are electric load, each one of them is trying to get into a situation where the least amount of energy is being expressed. That's what it tries to do. When it's out of sync, when things are off kilter, that's when the magic happens, so to speak, and things get crazy until it finally finds a nice balancing point again. I think that seeing some discharges in slow motion, I mean, we looked at the center of the galaxy, it looks like there's some going on there. I suspect the end of another galaxy, a Seyfert galaxy, would have something like that if we could zoom in, but I don't know how far away one is to us, so, or how long we'd have to wait looking too.
It just seems like a good way to test our hypothesis and some of our. I mean, you don't have to have it going from planet to planet filamentary, to have huge electric storms like you were talking about, because it could still be planetary and have these huge arcs, I think, with these electrical discharges, but it doesn't necessarily have to be planetary. But it's a good way to test if that hypothesis is true.
Well, I think that we see it from time to time when we blow up space shuttles and other things like that, where we start poking electrical, or I guess it'd be, for lack of a better term, probes into things. But even that's a much smaller scale, and we can control that. Trying to do it at a galactic level, or and how long would they take to go off? It would be like waiting for a quasar to be born.
Well, that's where it gets into this time scale thing.
Well, yeah, these things are huge. I mean, the amount of time it takes to do some of these things, and the event that birthed them would be massive but short-lived, much like, 1987A there, the supernova. Yeah. Because you can, witnessing that...
It's more in our time frame, obviously.
Well, yeah, but most of them follow the same type of thing. Like, we notice that gamma ray bursts follow the same amplitude and fall off as a lightning bolt. So there's a big upward swing and then a slow decrease on a curve. And that's what we notice with the 87A as well. It comes up and then goes down like that. These are just our interpretation because no one has a clue what those things are.
Mm-hmm.
But the end result, they think they're aimed at us or something, I don't know.
Those artists, god damn it.
Goddamn artists. Can't trust them. They're always making stuff up.
They always making trouble.
They're always making trouble for us establishment folk.
That's right. That's right.
Anyway,
just whatever.
but in the truth of it, we seeing that they follow a certain curve, like if you look at maybe you could put luminosity curve behind the gamma ray burst, and maybe it will give you the chart, because you're really just looking for a graph, and the graph, like that. So you get this up, you get an up and then a down, much longer down, and that's where that happens with almost every charge discharge. They follow a certain pattern. They go up till they hit their peak discharge point, and then they come down on an angle as they discharge, and the power decreases. It's the same thing if you have a lightning bolt, and it goes pow, 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 like that, with several little pows afterwards,
Right.
And
but it looks like here's one exponential. Here's an exponential that's a larger version of it, and here's another one that's going to happen.
Oh, they're not even, of course not. But if you go to the next in this,
there was all different ones.
Yeah, look at the one right beside. That one's a good one, or the one right beside it with the bell curve type look to it. No, the other one.
Oh,
See, it was trying to say exactly. It's giving you but those kind of graphs are just
smooth.
Yeah, they're smoother versions of the same thing, really.
Yeah,
but they all follow that same pattern. Those patterns follow with gamma ray bursts. They follow with lightning bolts, and they follow with supernovas. If you go look at supernova 1987A, I think they recorded over a period of weeks, I think, and it gives you an idea on how it came up and went down again. Obviously, not everyone is going to follow the exact same pattern, but you get the general idea how they
Right.
This is the trouble with electricity, you see. It's like, well, it should do this. Well, if it's a gaseous form, we don't know exactly. It's not going to be exact every time. But a lot of them, as you can see, have that very similar discharge pattern. So
Right. I mean, the one that you remember, the one where they're starting to trying to tie in the positions of where those fall, right? That we were looking at. That one is kind of compelling, particularly from kind of a harmonic, aspect. Just take a quick scan at it, just for reference. I believe this is it. Let's see. Yeah, because they're considered random.
Well, they consider random, but we also we don't even know where they come from. Like,
Right.
are they on the border between are they at the heliopause, or are they further off into space?
Mm-hmm.
You know, are they? Because we don't. I mean, I
So there's a
think they come from.
distribution, right?
Yeah, and is that sort of like the same type of curve as like if one happens one place and another point happens in another spot? Like, see, are they
Yeah,
getting sequential
this is
bursts?
where
See,
they're-
they're having sequential
right.
bursts. How can
They
that
eventually
possibly
tie it
happen?
together into this. Yeah.
Well, if you're getting
This
sequential
one-
bursts, just let me finish on that one. If you're getting sequential
Sure.
bursts in a row, okay,
Mhm.
then if they're far off in space, you're watching 8 of them in a row all across, a swath of the galaxy or swath of the universe. It's much more likely that they're happening right here
Yeah.
around the sun, and in the heliopause
Or
area
around
across.
us.
Well, that's what I mean.
Yeah.
Yeah, and well, that was close enough. But we don't. We know there's
The
an active
sphere
layer
that we're
there.
looking out at, right?
And they as a current sort of spools up, you get one of those dense plasma focus, and it shoots proton electron in different directions for a very short period of time, and that's called a gamma ray burst. And it comes in we sense it, but that's all we sense from it. We don't sense anything else.
Uh-huh.
So it's basically a different type of discharge. It spools up things to the gamma rays and drops it back down, but we don't get any light from it. We'd see light if we were looking at gamma rays, but we don't see any light, in that little narrow band.
Uh-huh.
But it just gives you this idea that, if they're following across a pattern, then they're probably close to us. Because if they were far away, that would imply that, oh yeah, one happened in this galaxy over here, another one in this galaxy over here, another one in that empty void over there, another one in that galaxy over there.
Right.
That seems highly unlikely.
Yeah.
It seems much more likely that...
It's a pretty even distribution. I mean, this is apparently data that they've gathered, right?
So that would also seem that either they're coming from the very boundaries of outside of space, or they're coming from a boundary that's closer to us, and I'm just of that opinion. So
Mm-hmm.
I like that we found them. I mean, each one of them is, unique. So
Right. Right. Very cool.
So you said that they noticed a pattern, did they?
Well, over time, yeah. They build it into this pattern here, and this is a paper that came across. I found it interesting now as far as diving in and saying, okay, you can justify this. You can justify this. I don't know, but I mean that's
whose clock has 22 hours.
It's 22 divisions. It's not saying it's a clock.
No, I just made a joke. No, it's okay.
Okay. Oh man,
I'm trying to figure out what they're doing.
That one flew right over my head. Yeah. It flew right over my head.
Hey, there he is, back from his show.
Yeah, it's just ended right now. Oh, it was a long one. It was 2 hours plus. Okay. Yeah.
How did it go?
You're still here, right?
Yeah,
we are.
Yeah,
we are.
What are you talking about? The gamma ray burst distribution?
Yeah, again. Yeah.
Again? I don't think we talk about that much. That has to go with an again.
We talk about it. Well, we talk about it.
Oh, what? Maybe 2 or 3 times ever.
Okay. Well, I'm totally game. I'll talk about anything like 5 billion times. So.
We were debating where,
if that's possible. That's the question.
the
time travel
light distribution curve of gamma ray bursts, and how it's similar to lightning, and how it's similar to supernovas, and then relating that to their distribution in the sky as to how far away they are, and noticing that they've come in strings and stuff like that. Are they, where are they located in space in reality? Where are they shooting at us from, So, where are they bursting at? Why are they bursting there? That type of thing.
Mm-hmm.
So what's the action that we're seeing, and that's really the question. Well, I mean, one of the propositions of this paper is from 2012. It's considered random, right? But he's taking all these data points, right, that seem random, obviously.
You know that Earth also produces gamma rays during thunderstorms. There's a concept called terrestrial gamma ray flash, I guess.
Huh.
I forgot the exact term, but it's there.
I never heard of that. Well, I guess I heard they made X-rays, so I guess gamma rays is just depending on the power of the strike, I guess. How tight are the ions spinning in that magnetic field? That's all that really matters. I mean, that's what we know from microwave ovens and so forth. We can control it. It will be ours.
So he ties it down into, there's actually a pattern behind all of them. And he's putting this out here. And then he's got 22 divisions for some reason.
So it's like...
Does that equate to 23 because it goes back to the source point?
Well,
I think it would equate to 23.
Yeah. I mean, it's, major arcana, right?
Well, actually,
that's exactly what I thought.
Yeah.
Really?
If there's return, and it's cyclical, it's got to have a 23 because it's 22.
I was thinking of the 22-year cycle of sunspots.
Would count as
22, numerologically. It's definitely been there since Pythagoras for sure. So.
Well, 11 years for the sun solar reversal too, magnetic reversal.
Right.
So 22 years would be a full cycle.
Right.
Yeah.
I have to. Before I have any legs on this, I still have to dive further down into it and say, but it's an interesting, it's an interesting proposition at least.
And it's interesting that it does seem to be like remember those images we saw of the lightning on Earth and how we could watch it happen on like the east coast of the United States, and then you could also see a flash over in Africa, and then east coast of the United States, another flash in Africa, and back and forth across the entire ocean, and how much they're related. They have to be related. Like, I mean, when you see a line, all these linked sequentially like that, then yeah, they're related.
Mm-hmm.
They have to be. It's like they're trying to, certain parts in space are trying to discharge, or so, and that could be what's going on, where they're trying to get the energy for the sun through the heliopause. And this is what I was referring to with Jim. Like, is it really following this pattern? If that pattern is occurring, how is it influencing inside? Because outside we have a boundary layer that's stopping them from getting the direct current from going through that into the sun, because there's a capacitance layer there, right? So all these things play out in trying to figure out how does each one of these relate to the nature, because we're basically working with something we can't see. I mean, we have gamma ray bursts and a few flashes, and the Voyager space probe. That's all that we know about the heliopause.
But they're highly energetic, though, right?
So they're gamma rays, yeah, I think.
Yeah, you would say.
But how powerful are they? Because the strength of them depends on how far away they are, right? So if they're farther away, they're not nearly as powerful. If they're directed, like, for example, there's a boundary layer, say, the heliopause, and on one side is positive, the other side is negative, and it shoots at us just generally towards the center where the sun is, we would pick up on that, even if it's not aimed directly at us. Or is it radial? Is it bursting in all directions at once? This is the type of thing that we're faced with when we can barely detect these things. They just occur very quickly. I'm amazed that we have the technology to even have this argument. Like, I mean, imagine in 20, 30 years from now, what we'll be able to talk about. So,
right.
I mean, we got space telescopes now. So.
Dude, awesome.
Dude, space telescopes.
dude, yeah. I mean, it's the pilot wavy side kind of thing. Yes, just all this stuff. That's pretty interesting.
That's the little thing in water moving.
Right.
Yeah.
Just, you would think random motion, right? Let's get a little further here. Trace it out.
I had no idea you could do.
You start seeing the, here's where I start getting into the Bessel function, right? See, I'm always better with images, buddy. Right? So my verbal ability to capture it doesn't always get it, as you know. So
is that modeling, or is that the actual?
No, that's the data, I believe. Yeah.
I mean, is that the droplet of water jumping over the water?
They do it with sound. They're able to get that wild frequency to have this little bubble float. Right here, I'll let it play, and you'll see the explanation of it.
They drop a little droplet on top of water, and the surface tension bounces it, but then it's directed by sound.
Yeah, they're vibrating the pool of water itself, yeah.
And it's showing that there's a primary wave that all matter moves off of as a aggregate, as like a primary substance of something that we're moving off of, and that's what's guiding things. That's what this is, from what I understand. Right.
That's right. And the thing is, it seems like it would be random motion throughout the whole thing, but as you gather all the data, and then you get these things. Pretty interesting. Right. But as you gather the data, there's peaks and troughs within the thing.
Well, and this is the thing. Is there energy being pumped into this system that we're in? It seems that there is. I mean, given the...
I think they just bounce on their own. I don't know where David got the idea of sound directing them. Maybe it is.
No,
I'm
I
not sure, but
I didn't say that. It's direct. It's keeping the droplet from absorbing it.
Breaking. Okay.
Yeah. That's all.
Okay. Okay. But that's its natural path, and it itself creates that structure right there, which is the Bessel function.
It's very interesting, and reminds me of that thing that we were. Someone was talking about. Where does...
Well, it kind of looks like Don Scott's, Birkeland current.
Right. Exactly, it does.
This is exactly where Jake was telling me to look and telling me that this is where it's at as far as the connection between the Doherty set, the Bessel function, and the laws of physics. But yeah, I mean, this is a good spot to look. For sure, there's a lot of clues here.
This is the tie-in with cymatics, obviously. So.
When I started looking at the quantum versions of hydrogen, for example, and seeing how they form an hourglass shape with a disk around it, that's the clouds of where the electron's allowed to be, I guess, in the quantum version. But I don't take anything for granted now, because what I used to think was one way of looking at an atom is totally friggin' wrong. I don't know why they taught us that. Niels Bohr was an idiot. Right, fine. I'm the only one that has a problem with him, but doesn't matter. He's still an idiot.
I like Bohr's. I like Bohr's experiments. Bohr had some good insights and some experiments. He's definitely up there.
I'm being a bit of a jerk. His model was, I mean, compared to what we know about electron clouds now and where they sit there's like to call that an orbital is only because he still somehow has influence, because it shouldn't be called an orbital anymore. It should just be like the cloud of where they are. It's just, it's so, and this is very interesting. We never detect the electron outside of these clouds, but we do detect that water droplet moving from ring to ring, if you know what I mean, in what we were just looking at. So, makes you wonder, of course, then it's back to what is an electron. So,
well, it reminds me of Maxwell's some of his depictions and drawings on his ideas of electromagnetism. They look fundamentally like this. I mean, they're completely hyperbolic, and if you look at it, I didn't realize how geometrically precise Maxwell's drawings were, and they're beautiful.
Oh, yes, and they're like 140 years old.
They're gorgeous, and it's all geometry. You look at it, and you're just like, whoa, that's all hyperbolic physics. No.
Well, what I like most about his drawings and the way that it worked is that, number one, he was doing it without computers. He was doing them point by point. And he also, maybe you'll find one. Look for original ones like that he drew.
Maxwell, vortex geometry, electromagnetism, stuff like that is what I looked for. And it pulled up some really good images. Because his whole idea was that it's all based off of vortex. As far as I understand, his atomic model was vortex-based.
I don't actually know if we had an atomic model. We were just learning. I mean, they didn't call electrons at this point. When he made these drawings, it was the 1860s, 1870s. The electron became known as a particle in like 1905. So
I'm going to try to share some, see if I can get them here.
Yes, they were usually calling electrons cathode rays.
Yeah,
if I'm not mistaken.
Mm-hmm.
There's I did find them. They look very similar to that drawing right there on that book cover, which he had 2 points, negative and negative, and then showing the relationship. And by the way, when you're dealing with this, he's not in any way. He's just looking at the electrostatics. This is the thing that makes things interesting. When you begin to move that, like that minus sign along, and you move it, the minus and plus, I guess. If you move them, you create a magnetic whirl around it. The right-hand rule creates a vortex around it as it moves. That spinning vortex of magnetic energy will do other things and create induction and all this other stuff. That's the weird stuff that electromagnetism gets into. And
there you go. There's some images.
Plotting in 3D, man. That's from the 1800s with a pen.
I don't know what this one is. The last one, that one's strange, but it really gets my attention.
I dig that one a lot. Yeah.
It looks like how we would draw, for example, the magnetosphere of a planet or something. It looks similar to that. Two magnetic fields.
The toroidalness of it just really starts yelling at you.
But just to do that picture would take hundreds of hours of work, because each point has to be calculated. Yeah, by hand. You have to run each point to that theory. You're not a computer. This is 1800s. So you would have to, I couldn't do it. I'd be impressed. I don't. I'd be halfway through and go, you know what?
It's how you embrace patience.
It makes me wonder what caliber of a geometer is he, and also who else was influential at the same time that was drawing hyperbolic type scapes. Because it's clearly art led and art intuited. And when you read it, it's not scientifically precise like our science is nowadays. It's more general, and then people turned it into a science after he kind of collected it.
Well, actually, he's the guy that did a lot of the collecting. What he did is he took the Ampere's law, Faraday's, the rules of Faraday, and a few others. I'm not even sure all the ones, but there was basically he condensed them down to 4 different equations, and then reneged them to calculus. That was his service, and they became Maxwell's equations. But they're really, I mean, the laws of Ampere were discovered before by Ampere, but he
this
was
would
only
be
working
called
on
math nowadays. You know,
There
this
was-
would be considered math, not science. And
There
then there
were-
would be a bridge between
Well, actually,
the two.
it has to be science because it's describing something real, I guess.
There were more than
With a
4
lot of math.
equations, I believe,
That's cool,
initially.
Initially, yeah.
Because he worked in coordinate, form without vectors essentially. So the present form of Maxwell's equations was created by Oliver Heaviside, like 20 years later.
Mhm.
That's true. If I'm not
That's where
mistaken,
you have that's where you have the standard, like in the inclusion of.
well, and people
Faraday's
blame whether or
law.
not Heaviside cut something out of his equations. He cut out all this stuff. Every time I hear that, though, I hear it by people who don't know what the hell they're talking about and couldn't do the math on it anyway. I know because I friggin' can't barely do the math on that. So I'm impressed. But to say that you can reverse engineer Maxwell's equations through Heaviside, I mean, there are definitions
But
of what.
the math is just
Maxwell-
a model to describe something. Here, once again, we're looking at nature,
Well, true.
and it's like, and the math, the math is just. I will posit there's many ways to describe it mathematically.
Well, obviously,
They always,
there was
always
two
try
big
to get
ones.
the most compact one, but Maxwell's equations have been traditionally known to be unwieldy to work with.
I found them to be, well, you know what? To be
No,
perfectly
really,
honest,
I
I
know.
don't work with them. I work
Yeah,
with
no, I
Ampere's
know.
law still,
I
like
better
as
have
opposed
people who
to.
do.
Yeah. Because, I mean, I recognize the use of them, but.
Right. No, they're
in
very,
a physical.
it's very clean, and it's a big statement.
Particular, yeah.
It's a big statement.
Yeah.
Okay, we have just like E
But
equals
clearly, this is. You can look at his pictures.
we own this concept because we've got it so compact, and it's like, well, that's quite a you're demanding quite a bit of auspicious respect there, But when he was looking, you can see it here. I mean, I find this much more intuitive,
I don't know if that's one of his drawings. Honestly, I grabbed that somewhere along my searches, but it looks very much
This
like
is,
Birkeland currents.
Right?
Yeah, that is. Yeah, his is more
yeah.
precise and in boxes and stuff.
Yeah.
But you can see why fundamentally his atomic theory or development was vortex based.
Well, yeah, he's plotting out, I guess it would be the lines of force, electrostatic force at any given point. And that's what we're looking at, I think, in this.
Mm-hmm.
I think those are magnetic dipoles.
Well, in this particular case, it is, yes. But in most of the drawings, he's doing electrostatics, plus and minus. But yeah, I think in this case, you're right. This is very interesting because these magnets actually shouldn't interact with each other.
Why?
Well, because they're at right angles to one another.
It's a cylinder level, right?
Oh, okay. Okay, maybe.
No, it's a toroid.
It says 2 cylinders.
Oh, okay, gotcha.
I'd say that's a cross section then.
All right.
Yeah,
okay,
two dipoles.
That's very cool. You could try plotting them out see how good you were to physically do it, either by, putting a piece of paper and some iron filings on top, type of thing. Might be easier to plot.
Uh-huh. Mm-hmm. Very cool.
I'm just impressed that he went to the effort of doing it. I mean, these are the first computer-generated graphics.
By hand, yeah.
By hand.
Yeah.
Well, you look into Julia sets, and you look into the Mandelbrot and Cantor around probably the same time, and they're thinking along similar ideas here, at least geometrically.
Yeah. So
I think
the rabbit hole. Oh, go ahead.
I think the Julia set is composed of a lot of those dipoles. Basically, I mean, in my mind, conceptually.
Yeah.
They were so smart back then. I bet you we couldn't even read that book.
Try.
No,
It's
I mean
available.
we could,
the
but
beauty of it is it's there. Yeah.
1878.
Yeah.
Just without. Could you imagine trying to do stuff today without having a lot of these rules hammered out? Because I mean, it's amazing how accurate you can get.
Yeah.
With this nowadays, I mean, you can sit there by knowing what these guys have done for us and working out, and then it bothers me greatly when someone goes electromagnetism. That has nothing to do with astrophysics or whatever, or they might get dismissive on certain aspects of it. And I keep thinking to myself, do you know how critically we can manipulate this material? Like how much we know about it? Like I can tell you that there's probably a chip inside this computer here that is working to 9 decimals of specific power. You know, like they're 9 decimals of discernment on a voltage. You know,
right?
And I know it's going to be that way because that's going to generate the proper color for that monitor. You know, or whatever it needs.
Right.
You know.
Right.